So hi, today we will talk about the rotating MMF concept, and actually that is the basic idea of all AC machines, and today we will just make an introduction to that concept. But before that, let's talk about the ways to induce some voltage in a coil. So let's say you have a coil and you would like to induce some voltage in it, and how many different ways are there to induce voltage. So first, what we can do, actually you can have a single coil, and actually if you apply some kind of variable flux inside that coil, either you can have a magnet, I don't know, you can put it in and out, or you can apply another coil with AC excitation, so which is the basic idea of a transformer, which we have seen in the first semester. So actually if you have a changing magnetic field in a coil, that will induce some voltage. So you don't have to have any movement, but just a varying magnetic field. And secondly, what you can do is, it can be due to the conductor movement in a stationary field. So again, for example, you can have constant flux, and you have a coil that is moving in and out of that constant magnetic field. So again, which was the main idea behind the DC motor armature coils, or like the right hand rule, Lorentz rule. Okay, the other one can be the rotation. Again, you can have a coil and you can have some constant magnetic field. It doesn't have to move linearly, but if it rotates, okay, if it rotates, the flux linking that coil will be changing. So even if the magnetic flux is constant, our dA term here is changing due to rotation, so we will induce some voltage. And actually we will see that is like the main idea of AC motors, the rotation inside a magnetic field. So let's see a case of an electrical machine, because I'm using those terms, but don't worry, we will talk about those details later on. So assume, this is a normal synchronous machine, which we will be discussing on the next videos. So here you have the rotor, and in the rotor you have a coil. Again, that thing shows some current coming out of the page or the window, and that one is going into the page. So this automatically becomes an electromagnet, and that is why it has shown like with north and south poles. So if you have that kind of configuration, and let's say you have another set of coils like the red one, so the one side of the coil comes out of the window through here and then goes back inside that direction. So it is like that kind of a coil. So the rotor, depending on the angle, so actually once you rotate that rotor, it will induce some voltage in those coils. And the interesting thing, again, we will discuss it for today. So they are placed like 120 degrees apart. So this is that one. So, and the other one is moved here, the other one is here. So all of them like are moved in different positions. Okay, so we will talk about that one. And again, as you can see here, so this is one phase, this is the second phase, and this is the third phase. Again, you can ask why 3 phase but not 2 phase or 5 phases. And actually, we discussed that also in the first semester, and also we have like a separate video on the advantages of the power transfer per length. So please watch that video if you didn't watch already. So on a normal 3-phase, again, what we know is all those voltages or currents, whatever, in a normal system, they are balanced. So they have the equal magnitudes, they have the same frequency. Okay, it doesn't have to be like always like 50 Hertz in a motor drive. It can be different frequency, but all the frequencies of these 3 phases will be equal, and they will be 120 degrees apart from each other. So there will be like a phase difference of 120 degrees between these ones. Okay, so let's move on. Again, we discussed in that video, in the first semester, that you can get more power per unit wire length. So instead of using 2 wires, okay, you can just increase the cable length by 50%, but you can transmit 3 times more power. So it actually gives you more power per unit wire length. And secondly, we didn't discuss it in that video, you can get some constant power output. What does it mean? So for that, actually you can click that link yourself in the presentation. So that is what we have here. So here in the first one, you have a single phase system. Okay, so there's nothing fancy about it. There's some time axis, and here I just defined some voltage, and there's a current in phase with the voltage, but with a different magnitude. So I didn't do, again, nothing fancy. So that is just the multiplication of the voltage and current. So it just gives you the total power. So actually, if you look at the single phase voltage, so it is sinusoidal, okay, and if you look at the current, again it is sinusoidal, so there's a power factor of 1. They are in phase, and actually I can find the power, instantaneous power, by multiplying these two. So again, positive gives positive power, negative still gives positive power, and actually it is in the form of sine square, right? So actually, if you draw it, the multiplication of voltage and current, so you can get some, I'm talking about not the RMS here, but the instantaneous power. So that's why you can have some peaks. So in that case, it's around 30 kilowatts. And in regions, for example, during zero crossings, voltage is 0, current is 0, so those multiplication is 0. So you can get like a sinusoidal, not perfect sinusoidal, but sine square, but again, it is a peak and minimum values. So this is for single phase. So let's have a look at what happens in a 3-phase system. Again, I didn't do anything fancy. What I have is I have the voltages here. So it's all going with time axis. I have the second phase, third phase, and again the currents, and currents are in phase with the relevant phases. So basically you have that voltage, and that is the second or the third phase. This is the second phase. So they are all 120 degrees apart from each other, and you can have all those things again 120 degrees apart from each other. So once you multiply those things, all those one phases actually produces the same sine square waveform, but those sine squares are also separated by 120 degrees between each other. So then, actually here what we have in that graph. So actually you can have, that kind of waveform. I think it should be 0, but I don't know, the graph seems like going to negative. But there's something interesting happens if we add all those sine square terms, and actually I did it here as well. So this is the power of the first phase, this is the another time, so this is the power of the second phase, this is the power of the third phase. So in that column, again, I'm not doing anything fancy, but I am just adding up all these 3 phases, and as you can see, it is all the way constant. Okay, so it is as if, okay, in an AC system, instead of dealing with all those harmonics and that kind of things, the power delivered, total power delivered, will be a constant DC. So whenever one phase power is reducing, the other phase is increasing, and actually that kind of smooth power transfer is very useful for AC motors and that kind of things. Again, we will discuss it in detail in the following weeks. So this is the advantage for the constant power. Okay, but that is not the most important thing for this course. The most important concept for this course was the rotating MMF or rotating magnetic field. Okay, so you can generate a rotating MMF with a three-phase system, and that rotating MMF concept is the main idea of all AC machines. Okay, so what does it mean? Again, if you would like to just remember one thing from this course in the future, please remember that rotating magnetic field that we will discuss in this video. So before proceeding on the other derivations and equations, I would like to show you a simple example, a Coca-Cola motor. Actually, we have exactly the same setup in our labs, but unfortunately you will not have a chance to try it. But here there's a video, so let me start that one. So here what you have is just some, I don't know, induction motor stator. So again, it seems like a complex, but at the end of the day you have three coils separated by 120 degrees apart, and they are excited with some three-phase voltages. So they create a rotating MMF, and that rotating MMF, now you are putting a Coca-Cola tin, and that is an aluminum tin, so that is conducting. So once you put into a variable magnetic field, so this is becoming an induction motor, again, which we will discuss in the following weeks. So you see, so let's start again. So you just put it and it suddenly rotate. Okay, there is no magnets in that rotor, there are no electrical excitation in that rotor, and it is just an aluminum tin. So that is, the main idea of an AC motor. So how does it happen? So what is that rotating MMF concept? So anyway, let's move on, and let's start with the basics. So if you have a single phase AC, okay, if you have a coil with a single excited with a single phase current, so you get a time varying signal, and actually here you see like a phasor representation, and on the left you have a real-time representation. So you can either have the x-axis or y-axis, it doesn't matter, but actually once you plot that phasor, okay, once you plot that phasor, as you can see here, it creates a sinusoidal waveform, sinusoidal MMF, right? So then the second thing, again, so what happens if I excite it by DC? Okay, if I excite a coil with DC, like you have the coil here, if I have the DC current, so it just creates a constant MMF. But constant MMF where? Constant MMF, for example, it creates, you have a coil and it has the maximum MMF along its axis. So probably if you have a Gauss meter or that kind of sensor, if you bring it to here, then you will have the maximum amount of B, okay? However, if you start moving away from here, if you rotate along that direction or along that direction, you will have slightly less flux density, right? And if you, I don't know, somehow if you come like closer, becoming to the horizontal axis, then the flux linkage will be less. However, then if you are coming back to here, again you will have maximum value but in the negative direction. So again, if you think about it, it doesn't have to be in an air core, it can be an iron core. So actually you have the maximum B along the axis of the coil, and if you go away from that direction or the other direction, the flux density will get weakened. So what you can do, again, this is an assumption, it is more complex than that, but if you have an iron core, actually you can approximate it like that. So you can assume MMF distribution, there's not a time component because it is excited by DC, but there's a position component, and that position component is theta, okay? So if you can think theta like as a displacement along that angle, right? So the MMF doesn't change with time, but it changes with position. Okay, so then if you have the same coil, and let's say you would like to see the flux variation both in time and position. So what happens if that coil is excited with a sinusoidal current? So you will not have a constant term like Fm here, but there will be another sinusoidal term as a function of time. So actually it can be expressed something like that. So you have still a peak value, and you can have a position value, and also there will be another term related with the time. So if that thing is moving up and down, if you somehow measure the flux at the instant where the AC current just crosses the zero, whenever it is zero, so actually flux will be zero everywhere, right? Or for example, if the current is in the positive direction and if you are measuring the flux at zero angle, then maybe you are seeing the maximum value. But if it is like minus maximum current, then your top point becomes negative. In short, okay, if you mathematically plot that thing with respect to position and time, what you will see a standing wave. Okay, that expression is a standing wave, where again, you know, in the previous case we were talking about the rotational direction, but now it is plotted in a linear scale. So don't worry. So you can think the x-axis as the displacement or rotation, and as you can see, depending on the current direction, it is a standing wave. So using a single coil excited with AC, you can generate a standing wave. Again, it doesn't have to be perfect sinusoid depending on the flux distribution, but that is what we assume for now. Okay, actually that is a quote from Nikola Tesla, and actually he was really good at mathematics, you know, as well as implementation, and he was like thinking everything in terms of energy, frequency and vibration. So that is why, you know, his passion with the AC systems. So actually he invented the three-phase AC systems, and actually he derived like three-phase is the most efficient way to transmit electricity. I mean, actually he suggested to use of transformers so we can increase the magnitude of the voltage, but actually you can have the same transformers with single phase AC systems, but instead he proved a three-phase AC system is the most optimum solution. And actually there's a debate on like who invented the three-phase AC system, and actually there are like a couple of different independent researchers that came up with the same idea. So anyway, so at the late 1880s we have the concept of three-phase AC. So what does it mean? What is the concept with the three-phase AC and the rotating MMF? So actually I want you to look at, you know, that animation until you get hypnotized. Okay, so what you see here, let's look at the red one first. So red one is our phase A, and if you look at the phase A, it is a standing wave. It is the MMF generated by phase A, and it is just standing depending on where the phase A is. It is going up and down. So if you look at the green line, okay, that is phase B. So that is also standing. That is not moving anywhere else. That is going up and down at the same place, right? But there's some phase difference. There's also some position difference. The place where the red one maximum reaches maximum is around here, and the place where I don't know if the green one reaches maximum is along here, right? But they have both a both position difference and also time difference. And again the same thing with phase C. So phase C is again 120 degrees physically apart from other phases, and also the time is also 120 degrees shifted in time. So they are all going up and down at different places at different times, but all those three phases are generating standing waves. Okay, so what I want you to have a look at is to the black component. So black component is the resultant MMF. So again, there's nothing fancy about it. You can pause the video and you can check it. So actually at any instant those bars are added, algebraically. So they are added on top of each other. If there is negative, they cancel each other. So you get the black line. So what kind of a wave does the black line? So it is not standing wave, it is a moving wave, okay? And its magnitude, apart from the other one, their magnitudes are going up and down up to 1. So they have a peak value of up to 1. But the black line has a maximum value of 1.5, and it stays at 1.5 always. It is not standing, but it is moving. And again, this is plot on a linear scale, but you can think like it is a electrical machine. So 0 degrees, 90 degrees, 110 degrees, 380 degrees. So that wave is kind of moving. So suddenly you created a rotating MMF without any moving parts. So it is the same thing as like you can have, for example, you can have an iron piece in the rotor. Let's say my hand is an iron, and you can have a magnet. So you move magnet here and it will follow to that one because it would like to move to the minimum reluctance position, right? So you move here and it will move back to here. So if you move here, it will follow that one. So but in order to move that magnet, so you need some physical connections, I don't know, some gears or someone is going to move. But actually that waveform shows us without any moving parts, just using coils and a clever way of exciting those coils, the MMF will have the same effect as rotating magnet. So it is where the term comes, rotating magneto-motive-force, or in other words, that the equivalent magnetic field of all these three stationary coils create the same effect as taking a magnet on your hand and trying to rotate with some speed. Maybe it will be clear with the phasor diagram. So this is a real-time representation. Let's see what happens with a phasor. So that is exactly the same thing, but in phasor diagrams. So here again, first let's have a look at the red arrow. So it is the phasor representation of that standing wave. So its axis is not changing. Its axis is always between 0 and 180 degrees, but its magnitude is sometimes 0, sometimes it is going to the minus maximum, so on. And the same thing is there for the green one. So green one is again shifted like 120 degrees from the red arrow. So phase B is moving up and down along its axis, and the same thing is there for the phase C. Again, you can pause that video anytime and you can add those vectors, and the resultant will be the black one. Okay, the vector addition of all those three MMFs will give you the black vector. And again, there's something nice about the black vector here. Its magnitude, again it was moving like 1.5 here. Its constant magnitude here. Again, its magnitude is not changing. It is constant at 1.5, and its axis is actually rotating. So there is no difference. So it is the same thing like holding a magnet, moving up. So my magnet is at top. So then I'm bringing it down. So in that one, I'm at 180 degrees. So I move it slowly. It's coming down and it's going up. So again, that thing is kind of slow here. So if you are exciting it with like 50 hertz, that thing is making like 50 rotations per second. That MMF is rotating at 50 hertz, quite a fast rate. Okay, so somehow, I mean, if you can generate that kind of MMF in the stator, and if you put some kind of rotor, it can be a reluctance motor, it can be a permanent magnet rotor, it can be, I don't know, salient or cylindrical rotor, whatever. So all that thing is going to do is try to catch to the minimum reluctance position, as we have seen in the previous weeks. But once it reaches to the minimum reluctance position, so actually the MMF has moved, so it will try to catch that thing continuously. So it is, you know, I will show you the slice is totally donkey and carrot relation. Okay, so here actually you see, you know, both of those, the real time and the phasor representation together. So again, you know, I want you to look at those animations until you get hypnotized. Okay, cool. So now, you know, that is okay, the nice things, but how does it happens? Okay, how we can prove it? So again, you know, it's kind of boring, but quite important. Let's try to derive it. Okay, I will try to derive it, and I assume, okay, I have 3 coils separated by 2p/3 physically between each other, and they are all excited with 3-phase currents. Again, there's a phase difference in time with 2π/3. Okay, so let's. Okay, so what I can do, again, you know, I'm just multiplying those angles. So this is the currents, and I would like to calculate the MMF waveform. So I can represent the MMF like the time part and also the angle part. And actually, I think I have written it wrong here, so I will fix that. So there will be some phase difference as well in those time components. Okay, so let's derive that. Okay, so I have written here the correct term, and I have the phase A, MMF of phase A is equal to Fm is the maximum value depending on the current and the number of turns, and they are, you know, both the current directions and the coil dimensions are equal. So we have the same maximum Fm between those phases, and physically, you know, let's say this A phase is aligned at the 0 angle, so that is aligned at 120 degrees, this is aligned at 240 degrees, and depending on their physical positions, the current excitations are time shifted as well. So again, here I would like to find what is the total term. If I add all those, you know, 3 standing waves, how can I obtain a constant magnitude waveform? So that is what we would like to derive. So let's continue with the derivation, and here what you can again write, because here like there's a multiplication of 2, you know, cosine terms. Again, you can do the same derivation using the signs. That doesn't make a difference. So for those who don't remember, so the multiplication of these 2 cosines can be written as like 1/2. Okay, the difference, or like difference of those cosines plus half of addition of those 2. So I will write the same thing using that term. So I can write F total, okay, is equal to Fm is like a constant term for all of those things. So I am taking it to the output, and I am writing that multiplication like that, right? So it becomes 1/2 cosine, okay, theta minus that one, theta minus omega t, plus 1/2 cosine theta plus omega t, right? So then I will write the same thing for that derivation. So it becomes 1/2 cosine, okay, theta minus 2 pi over 3, okay, minus omega t, minus minus it is plus 2 pi over 3, okay, plus 1 over 2, okay, so then the addition of that one, theta plus omega t minus 2p over 3 minus 2p over 3, that becomes minus 4 pi over 3, right? Again, as you can see here, that one and that one gets cancelled, so that is theta minus omega t, but here they are added up. Anyway, let's write the last term, 1 over 2 cosine theta minus 4 over 3 minus omega t, minus minus becomes positive p over 3, okay, plus 1 over 2 theta plus omega t minus 4p over 3 minus 4p over 3, it can be written like 8p over 3, right? So that is the whole term, and again you can see here that one and that one, you know, cancels each other. So let's move down. So let me write it for sake of simplicity. F total is equal to Fm. So now, so this is theta minus omega t. This is theta minus omega t. That is theta minus omega 3. So these are all adds up, right? So it becomes Fm 3 over 2, okay, times cosine theta minus omega t. These first terms, 1, 2, 3. Okay, plus, then what happens to the other ones? Let's write those things for long. Cosine theta plus omega t, and plus, okay, write it like that, plus 1 over 2, there will be, sorry, some cosine here, cosine theta plus omega t minus 4p over 3, okay, plus 1 over 2 cosine theta plus omega t. What is minus 8p over 3? Okay, so actually I can add like 2p on that one and nothing will change, so you can write minus 8 pi over 3 plus 2 pi is equal to minus 2 pi over 3, so it makes a full rotation. So actually I can write it like minus 2 pi over 3, right? So what is the addition of all those three parameters? So you can think the first one like that one, okay, the second one is like that, and the third one is like that. Okay, so the first one will be 0, so this is, you can say, minus 2 pi over 3, and again this can be minus 4 pi over 3. Actually, if you add all those three terms, or you can think them like a phasor, and they all cancel each other. Okay, they all cancel each other. So those terms are gone. So what we left with is we have F total is equal 3 over 2 Fm times cosine theta minus omega t. So that is the resultant vector mathematically, right? So we started with, you know, multiplying all these components, and the first terms actually having the identical term, they all adds up, and instead of 1 over 2 you end up having 3 over 2, which is coming from 3 phase. And then the second ones, they are the same magnitudes, but they are all separated by 120 degrees. So they are like, you know, phasors, they are like vectors, having each magnitude same but an opposite direction. So if you add all those 3 vectors, they cancels each other, and actually you get 0 from the second term, and that is what you obtain. Okay, so that is the same term making the, you know, MMF rotating, and its magnitude is not 1 but 3 over 2. So again, you know, here you see again, sorry about that, I will fix that in the presentation file. But once you add those things, you have that waveform. Actually, you know, you can see there's some animations here. So let's try to open up, and you can play it yourself. So this is not with the sinusoidal. This is not with the sinusoidal, but just as a square wave, but it is still the same waveform. So again, if you have some phase A, so it is coming like going up and down like that. Let me get rid of myself. And if you just put phase B, again there's some kind of animation here. But if you have all those phasors at the same time, again this is just a representation, not perfect sinusoid but using squares, but you can see how you can obtain that kind of things. Okay, and actually here you see all the possibilities. Instead of just using the first harmonic, or you can add different harmonics, so it is, you know, Fourier series expression. Okay, so anyway, to sum up, so we have 3 over 2 is coming from the 3 phase, and like you add 1 over 2 term 3 times, and that is the maximum MMF, and that is the term that we are interested in. So that is not a pulsating wave anymore, but it is a rotating MMF. And actually you can do it, doesn't have to be just for 3 phase. If you have a 5 phase system, you can still have the rotating MMF, but in that one like it will be not 3 over 2, but it will be 5 over 2, or in generalized case, if you have M phase shifted by of course 360 divided by number of phases. So if you have a 5 phase system, each phase will be shifted like 72 degrees between each other. Anyhow, if you do the same operations, you will find M phase divided by 2 Fm times cosine theta minus omega t. So that is really the basic idea of all electrical machines. So you are creating a rotating MMF. So that is what you get from the rotor, and actually the rotor itself try to align itself to the minimum reluctance position, because it doesn't know if there's any AC system or if there's any permanent magnets. It just tries to come to the minimum energy position, trying to minimize the reluctance or maximize the mutual inductance and that kind of effects, as we discussed in the previous week. But once it comes closer, the MMF already moved. It comes closer, the MMF already moved. So that is the idea that, for example, in the synchronous machines, the rotor is rotating exactly at the same speed with the rotating MMF. Okay, so again, you know, there's nice debates between, you know, Edison and Tesla, and again, like Edison's motto was to, you know, more experimental side. So you can try like many different ways of doing that, and actually he invented like, you know, many devices, including the light bulb and that kind of stuff. But Tesla's motto was more on building everything like mathematically, using power of the, you know, those frequencies, Fourier series, that kind of representations. And actually, like he was saying, like you can use mathematics, so it can eliminate like many unsuccessful efforts in your experiments. Okay, so that's all for this video, and we will talk about the synchronous machines in the next video. Okay, thank you.